Mostly so far we've graphed things on a scale that shows y and x on these axes, and often we have them going into negative as well, of course. But what we're going to find in this unit is that a lot of the time we're looking at rates of change and we're thinking about how things change over time. So we're going to more and more often see t on this x-axis because we're interested in what's happening as time's passing. And what we get on the y-axis, it's going to vary. We could be looking at a population and it might be big P for population, or it might be T for temperature, or it might be V for volume, or anything that we're investigating. So get used to seeing different letters on these axes. Now, the reason that we examine rates of change is because we're often really interested in the rate more than just what's going on at the time. So let's look at these examples at the bottom. Here I have a graph of distance over time. Now, we know what distance over time is. It's speed, isn't it? So if we go d over t, let's call that big D for distance, what we get is speed. Okay, and you'll notice that d over t, I've got distance on the y-axis and I've got time on the x-axis. So if I have distance over time, I've basically got rise over run. So speed actually gives me rise over run, and that is gradient. And differentiating a graph tells us what the gradient will be at any one point. So if I'm to graph somebody, say, running maybe 100 metres, let's make this 100 in, I don't know how long, let's say 15 seconds. If they were running like this, I can analyse their speed at any one point. Now, where are they running the fastest? They'll be running the fastest when speed is the greatest, and that will be when the gradient is the steepest. So if I put my pen on the curve to analyse the gradient, I can see that around about here, it's very steep. The gradient is the highest, so that would be when they're running the fastest. Whereas I can see here, speed or gradient drops off a little bit, so they must be perhaps getting tired here and not increasing their speed at this point. They're actually slowing down. They're still moving along. As time ticks along, they're getting more distance covered, but they're slowing down from this point. So down here, they're obviously speeding up, especially from the beginning where the gradient looked like it was 0, because perhaps as the starter said go, they were stationary for a little while before they actually took off. So if I'm analysing distance and time, it's all very well to say where was I after 5 seconds or 5 seconds here, and I could read up and across and work out where I was. Or I could say, how long did it take to run a certain distance, and I could read across from that distance and down and see when I was there. But we're often looking at the actual rate of change. So we're interested in speed, and that means gradient. This example over here, I have volume versus time. So perhaps in this scenario, maybe we've got a tank filling up, and I'm looking at how much water is in the tank at any one time. So I start with a certain amount of water. More water comes in until I reach quite a lot of water, but then the water seems to be flowing out. Now, if I was to graph volume over time here, what I'm actually getting is the flow rate. So if you said to me, well, when is the water neither going in or coming out, it's just stable, I'd say here, because at that point right there, the volume's not going up or down, it's actually levelled off. A lot like down here where we have a stationary point where our runner hadn't started running yet. As far as water coming in goes, I can see that in the beginning here, the gradient was steeper than it was a little way into the experiment. So probably water was flowing in fast here, and then it's gone down to maybe a tiny trickle until no more water's coming in. And then we maybe have a trickle of water going out. The water starts flowing out a bit more and a bit more until then the gradient is so steep, it's obviously gushing out. So the steepness of the curve tells us so much about what's happening, and that's why finding the derivative is such an important skill. Now, let's look at some things that we should already know, but we might not have sort of thought of before. If the derivative, f dash a, now I've written a there, not x, because we're looking at some point, say x equals a, and we're saying, all right, if you analyse the derivative at some point, a, and it's greater than 0, in other words, it's positive, well, what does that tell you? It tells you that the gradient of the curve, y equals f of x, is positive at that point. And so we say that f of x is increasing. So we can see here that f of x is increasing throughout this entire run because the person f of x, which is distance, the distance keeps on increasing. As time goes past, the runner gets further and further along, whether they're speeding up or slowing down. And over here, we can say that our curve was only increasing from this point to this point, because that's when the water was flowing into the tank. In other words, f of x, or the volume, was getting bigger. Now, if your derivative at any point A is less than 0, in other words, it's negative, then the gradient of your curve is negative. So we say that f of x is decreasing at that point, x equals a. So we could say that the volume is decreasing for this whole section. And how do we know? Well, the gradient is negative that whole time. So the change in volume over time is actually going down. Now, what about if the derivative at some point A is equal to 0? Well, we found it was here where we had horizontal gradient, and here we have a horizontal gradient. And we call that something special, call it a stationary point. Stationary means nothing moving, so this sort of makes sense because here time is ticking along, albeit in just milliseconds, before our runner starts to move. Our runner is stationary. And at that point, we see that f of x, or whatever it is that we're measuring on the y-axis, is neither increasing nor decreasing. It's stable there, even if just for a moment at that point.